Yeah, hello everybody, my name is Christian Stein, I'm working for Fraunhofer IGD and Technical University of Darmstadt in Germany. And this is my talk about the use of spatial data structures on the web. Quick outline, I will start with the application area and some specifics on the web environment. Then I give you a quick overview on how spatial data structures can be used for visibility determination. I will show you how we integrated the data structures into Freedom and our evaluation framework, how it looked like. And after the evaluation and results, I will show you a short demo of our current work. Okay, we are targeting on large model visualization on the web. And the focus here lies on continuous interaction for an interactive user experience rather than immersion. So the correctness of the resulting image is not that important. Compared to games, like we have 3GS on the web and other more or less engines you could use to make small games, our bottleneck is on the vertex side, meaning that we do not need complex lighting, materials or effects, but instead we usually have one color per entity, maybe some color coding or highlighting. But instead we have a distinctively higher polygon count. We are targeting for the browser as standalone presentation platform, because that way, if you do not need to install any plugins, you don't have licensing costs, and you can easily update your rendering software as well as your data by simply pressing F5. And it's easy to add features like sharing and collaboration, which are everywhere on the web. The web environment has some drawbacks. For instance, JavaScript has very slow processing speed compared to native applications, and the garbage collection could kick in any time, reducing your frame rate. And furthermore, WebGL has a limited feature set compared to current OpenGL versions, and is slowed down by a list of intermediate abstraction layers from the WebGL rendering context down to the communication with your graphics adapter. Therefore, one could suggest that the web environment is a bad fit for large model visualization. So we try to mitigate those drawbacks. For once, we use ASM.js, which is a subset of JavaScript. It creates objects on its own type array, and after the source has been downloaded, it is ahead of time compiled, so it trades in JavaScript's flexibility for performance. This meant that we had to implement all of our software twice, once in JavaScript and once in C++, which was then cross-compiled to ASM.js using mscript. Secondly, in July last year, Mozilla started the experimental and prototypical implementation of the WebGL 2 rendering context, which is available in the Firefox nightly builds. And this introduces some advanced features like hardware occlusion queries or instancing. On the other side, on the right, you can see how cross-compiled code looks like, which is almost impossible to write manually. So I'm coming to visibility determination, and the general goal is to decrease the number of polygons that you are rendering, and you can do that by discarding not or barely visible elements of your scene. And we shifted the decision level for the visibility determination from the polygon to the object level, meaning that we decide for every object in our scene if we render it or not. We evaluated two conservative culling techniques in the paper. For once, hierarchical view frustum culling, and secondly, occlusion culling based on the coherent hierarchical culling ++ algorithm. We're using the spatial data structures to exploit the spatial and temporal coherence in our scene, and our focus lies on fast construction of the data structures. Compared to ray tracing, where they have been evaluated in depth, we are using small hierarchies with only a few thousand nodes, and we're looking for a good adaptivity for the data structures to adapt to the geometric density distribution in the scene. And there are two classifications of spatial data structures, regular and irregular ones. And we picked a candidate from both classes, which were the octree for the regular ones and the bounding interval hierarchy for the irregular ones. And as a building heuristic, we used spatial median split. This is how we integrated the spatial data structures into X3D and X-Freedom. For the user to easily identify the parts of the scene which should be processed by the spatial data structure, the respective X3D description is wrapped in a static group node, which you see on the left. If this part of the scene becomes visible during traversal of the scene graph upon initialization or updating, we collect all the drawable elements from the subtree, and we break up the semantic structure of the scene graph and create our own optimized representation, which is the spatial data structure, which then we use on a per frame basis to accelerate the visibility determination. During traversal, we collect the set of visible elements, which is normally a lot smaller than all elements in the subtree. Okay, our evaluation targeted at a few topics. For sure, we evaluated the candidates against each other. Then we evaluated two execution environments, which was standard JavaScript versus the cross-compiled ASM.js version, within two browsers, Chrome and the Firefox nightly builds. And of course, we evaluated the trade-off of the culling techniques, which is comparing the determination costs, how much calculation did we spend on determining if an object is visible, compared to the rendering cost if we had just rendered the object. Because for sure, if it takes more time to find out if an object is visible, we could have just rendered it anyway. So I'm going to show you quickly how our evaluation framework looked like. We see the power plant was in the scene, and we can look at how our data structure was constructed based on the bounding boxes of the drawables. I hope you can see that on the left side. We can change the different parameters. We can switch between the ASM environment and the standard JavaScript environment. We can recompile our data structure on the fly. And on the right side, we see some statistics. And then our evaluation walkthroughs consisted of a list of X3D viewpoints, which we cycle through. And we store the statistics for the different tasks we have to execute, the amount of nodes we traverse, and the effects of the different culling techniques. And after the walkthrough, we can download the resulting data in an Excel sheet. Some short facts on the evaluation before I go into more detail on the culling techniques. The ASM.js environment proved to be way more efficient than JavaScript, outperforming it at a huge factor. Firefox was a little bit faster considering the calculations, but the overall rendering performance in Chrome is better, so you cannot really give a result on this. Considering the construction, we were looking at the possibility to reconstruct the data structures on a per frame basis, but this was only possible up to a node count of 1,000, which simply was not enough. Both data structures showed a good adaptation to the geometric distribution. We tried to find the upper bound on the amount of nodes that we can traverse on a per frame basis, and without any additional calculations for the culling techniques, using ASM.js we were able to traverse 25,000 nodes. So this was more or less the upper bound on how big our data structures could grow. The evaluation of the culling techniques during the walkthrough, we can see here for the few frustum culling, and in our experiments the best frame times and thus the resulting frames per second were always between 5 to 10,000 nodes. If the node count got too high, the additional calculations didn't pay off anymore, but if the node count or the spatial subdivision was too coarse, the few frustum culling simply was not efficient enough anymore. I don't know if you can read it, but the blue line and the green line show the percentage of traversed nodes during the walkthrough, whereas the red and the purple line show the resulting frame times. And for the bounding interval hierarchy, increasing maximal depth didn't generally increase the amount of calculations we had to perform, because new nodes are always added as children for existing nodes, but introduce only additional calculations if those nodes were lying at the boundary of the few frustum. Whereas for the octree, depending on the subdivision strategy, with an increasing node count, the frame time almost increased infinitely. Coming to occlusion culling, in the plot we see a comparison for different depth levels of the octree and using different culling techniques. The blue line in the top is the frame time for few frustum culling using the octree of level 5, whereas the green line was for the octree of level 4, which showed significantly better results. And if we combined few frustum culling with occlusion culling, the purple line is for the octree of level 4, and the red line is for the octree of level 5. And we see that, with the addition of occlusion culling, we could employ hierarchies of node count which we had not been able to render an interactive frame rate before. Further, we compared our data structures. Here we see the comparison of the octree and the bounding interval hierarchy during the walkthrough. And if you remember the short walkthrough I showed you, we always set up our walkthroughs that way that in the beginning we started with the camera outside of the model, then started a walkthrough flying inside the geometry, and at the end we returned back to the outside. The same is true for the data of this walkthrough, and you can see that the octree generally showed a lower and more constant query time, which is the blue line, compared to the green line, which is the query time for the bounding interval hierarchy, and the red line is the resulting frame time for the octree, compared to the purple line, the resulting frame time for the bounding interval hierarchy. And what we found is that the octree was considerably faster while the camera was moving inside the model, whereas the bounding interval hierarchy showed a better performance at the beginning and the end of the walkthrough when the camera was outside of the model. Quick summary. Both data structures performed well in accelerating the visibility determination, but the best fit is always case dependent, how your scene looks like. We saw that using these spatial data structures allowed us to use more complex culling techniques like occlusion culling, which you simply cannot use on a scene graph structuring. ASM.js speeded up our calculations a lot, but the biggest performance boost came from the use of hardware occlusion queries from the WebGL 2 prototype, which even enabled us to use hierarchies with much higher node counts than only using few frustum culling. Future work, we're looking into optimized implementations because at this point to ideally compare the different structures, we used node representations, the same node representations for both data structures. We didn't look into updating or reconstruction of the data structures yet, and not only heuristics on when to do so. We're thinking about an adaptive control for our parameters, like the traversal depth of the traversal data structures, and we want to combine our data structures with a level of detail. Ideas like, for instance, the pop buffers we introduced in Xfreedom. The previous demo you have seen was a prototypical implementation in Xfreedom 1.6, which has not been published yet, but we're working on integrating this technology as a basic feature in the upcoming 2.0 release of Xfreedom. Yeah. I will give you a quick on this here. We see a number of the power plant model rendered with the upcoming Xfreedom 2.0. We see the data structure we use, additionally to occlusion and.
Is that the octave? Was that the octave?
That's the octave, right? Additionally to few frustum and occlusion culling, we are using small feature culling here, and we're using the source containers Max was talking about. As you can see, it's additionally loading geometry as soon as it got visible. And every part of the power plant models is selectable. Yeah.
Yeah, the yellow boxes are...
Right, the yellow boxes show if the geometry is not loaded yet. And as soon as it's loaded, it's pushed directly to the GPU.
How many polygons did you build?
Sorry?
How many polygons?
Each of these power plant models consists of 12 million polygons. And we have 9 of them in this. Okay. Thanks for your attention. Are there any questions? Yes, please.
Can you say a few more words about how you build your data structures? And I'm a little bit surprised that the octree is higher performant if you can only do 1,000, rebuild 1,000 nodes per. Seems rather slow.
Yeah, as I said, we do not have used any sophisticated construction algorithms yet. For instance, for the bounding interval hierarchy, there are faster ways, and the linear octrees as well. At the moment, we just rasterize all the drawables into the octree, meaning we start with one root node, and we add drawable considering its bounding box. And it's passed through the existing structure until it reaches a leaf node, and if one of the possible child nodes would contain the whole box volume, we just add those child volumes as long as we have not reached our maximal depth, which we set as a parameter initially.
Any other questions over here?
How much does your view frustum performance depend on the model?
I think it mostly depends on the walkthrough, like where your viewpoints are set, because definitely if a large part of your scene is outside of the frustum, the culling doesn't need a lot of calculations, but if you have the whole structure within the frustum, it takes up more time, so we cannot generally answer that question. I think we have a lot of statistics in the paper. You can look them up and we can talk about it. Yes, please.
When the camera is outside of the factory, is the objects inside the factory purely caught by occlusion culling?
No, the occlusion culling is combined with field frustum culling, meaning that only nodes which are inside the frustum are used for the occlusion culling algorithm.
Okay, thank you very much, Christian.